It's undeniable that metagenomic sequencing has catalyzed our understanding about the gut microbiome. We know about the structure, we know about the connection with human health, and what is more interesting, we know about dynamics and how universal that dynamics is in human beings. So as explained in this beautiful paper, this has somehow raised this promise of personalized medicine. So here is the idea. So gather some data from experiments combining different bacteria, plug that data into the computer and do some mathematical modeling like using the generalized Lotka-Volterra, and then extract the interaction network. The good thing about this is that if you want to target, let's say, the yellow bacteria, then the only thing is that you have to somehow provide some food to this other bacteria and then ecology do the rest. In this framework, we can go from macroecology and using these mathematical models to microecology. But can we really do that? Not so fast. In this presentation, we will give you 3 reasons why macro-level mathematical models cannot capture micro-level dynamics. So let's begin. First reason, most experiments are at a steady state. So take one equation, for instance, the generalized Lotka-Volterra, we have m plus n squared parameters. The thing is that at steady state, at most we have n data points. So we have an undersampling problem, so we cannot infer all the parameters. There is one caveat. You can do better, you can do like in this recent paper, instead of putting all the bacteria together, you can do all the combinations, all the patterns between one bacteria alone to all bacteria altogether. In that case, in principle, you can infer this matrix. The thing is that you have 2 to the n minus 1 equations, and that means that if you want to extract pairwise combinations, you need at least 5 bacteria. If you want 3-wise combinations, you need 8 bacteria, and so on and so forth. And this is very costly. Reason number 2, chemical experiments are noisy. So let's do a numerical experiment. So take some parameters, then simulate, in this case, 3 populations, add some noise, try to resemble what happens in the experiment, and try to do some Bayesian inference on top of that. You can see that the inference method is working. So basically, we are capturing the dynamics and also the uncertainty related to the data. The problem is that you want to take a look at the posterior density, starting with a random seed, and basically you want to infer what is the probability of the parameters given the data. You find something like this. Take a look at this parameter. You can see that the mode of the distribution is close to the vertical dashed black line, which is the original parameter, but there is one problem. So you can see that the original parameter was negative, and we have a large probability of that parameter to be positive. So what are the implications for ecology? So if you take a look at these 2 panels, you can see that there is a probability that the prey becomes a predator and the predator becomes a prey. So our interpretation of this connection between bacteria is not that simple. Reason number 3. The experiment don't carry that much information. Take a look at this graph. This could be the time course of a bacteria evolving over time into the gut. Now, ask yourself this question. How many pieces of significant information are there in this picture? So let's count. So maybe the steady state from piece of information, the distance from peak to steady state, of course the location of the peak and the width of the peak. Okay, these are 4 pieces of information actually. So if you have n populations, you can expect that at most you have 4n. Of course, if you have enough data, maybe you can capture the curvature here. So at most you have 5n parameters. So let's do the math. So the orange curve is this upper boundary, which is called 4n. The green one is the more conservative one, which is 5n parameters, or pieces of information. And the blue dashed line is the number of parameters in the Lotka-Volterra model. So you can see that above 3 or 4 populations, you're doomed. So basically that means that maybe you can identify the parameters, but you cannot interpret those. Why? Because you don't have enough significant information in the data. This can be an explanation why in this experiment that we did before with this random seed, this Bayesian method basically is saying that you cannot learn anything. But now one question arises, can we prove this intuition systematically, or is this just a hunch? The answer is yes, and there is a name for that, and it actually is called the theory of sloppy models. This theory, developed by James Sedna and collaborators, basically says that maybe you have enough information to estimate the parameters, but those parameters are irrelevant in the big picture. So using these ideas, they develop a reduction method called the manifold boundary approximation method. The idea is the following. Imagine that you have a model with 2 parameters, and you have 3 experimental observations. In that case, you can create this manifold, which is a 2-dimensional manifold embedded in a 3-dimensional world. These authors identify that many models share this sloppiness property, meaning that you have some directions in this manifold that you can change the parameters systematically, but the outcome of the model doesn't change. So you can take original model and moving your parameters in this manifold, you can have simpler versions of the model in which you have 1 less parameter at a time. So we decided to apply this to the Lotka-Volterra model. So we did an experiment with 4 populations, purely deterministic and free of noise and uncertainty. So this is one outcome of the model. You can change the parameters, but the conclusions are almost the same. And we did it systematically. So we start with the full model. You can see that we have this m times n plus 1 parameters, and then we apply the model systematically. So we are removing 1 parameter at a time. So here we go. Apply the method once, and then you remove 1 parameter, apply it twice, and so on, and so on, and so on. And after you have removed 9 parameters, you can see that these 3 curves, the green, the red, and the blue, are almost the same, but the orange are somehow losing this ability to predict. But it can be shown that if you relax the condition, the initial condition for the orange one, you can actually remove this equation, so you end up with a 3-population model explaining all the curves, despite this point, with just 7 effective parameters. So if you remember this intuition that we say we have almost 4 parameters per curve, this would end up with 16 parameters. We have just 7 parameters, so this is clearly an upper bound. Another example, in this case with periodic behavior, in this case we'll go from 12 parameters to just 5 parameters. So is this a defect or limitation of the generalized Lotka-Volterra? Of course not. So many people argue that, okay, maybe we need to do things more complicated. We need to add the dynamics of the bacteria, but also the dynamics of the resources in which they are competing. But the problem is worse. Actually, if you take account this idea, how many pieces of information is in the data, of course you are making things worse. So sloppiness is not a matter of sophistication, it's a matter of actual information in the data. So are mathematical models useless? The answer is no, and one of us proved recently in this paper that you have to change the question. So instead of thinking about these microscopic interactions between bacteria, you have to think in terms of correlations, ensemble predictions, and populations. So in summary, first you have to do the math, so steady states are not enough. The second idea is that noise can spoil parameter interpretation, so you have to do Bayesian inference in order to know more about that. The third idea is that the sloppiness is prevalent in this sort of models, and it's not just a matter of model sophistication, it's about how many information is in the data. And the final take-home message is that you have to ponder what answers can your model provide. So you have to change the question that you interrogate the model, not just the model. So thank you very much.